In this video, I'll be giving a problem on the Carnot cycle and helping to set this problem up. In the next video, I'll go over the solution in more detail. So let's read the problem together. We have 1 kilogram of saturated water with a piston cylinder assembly that's going to go through a Carnot cycle. And the water starts off as a saturated liquid at 150 degrees Celsius. This is our state 1. And then expands isothermally at a constant temperature until it is all saturated vapor. This is our state 2. It then expands isentropically until the temperature has dropped to 40 degrees Celsius. It is then compressed at a constant temperature, and here the entropy drops exactly the same amount as it increased from state 1 to state 2. And this is our state 4. The water is then compressed isentropically to return to state 1. So note here, our state 3 and 4 are both the liquid vapor mixed saturated state. Sorry, this should be state 3 and 4. So, quick review. When I say saturated, when a fluid is saturated, a gas and a liquid phase can both exist at the same time. For a saturated fluid, if you know the temperature, you can also find the pressure from saturated tables found online. And here is a link to a saturated water table online that you will need to use in this problem. Okay, so how do we draw the 4 stages here to help visualize this problem? So in state 1, we've got our familiar cylinder enclosed by a piston. Inside we have liquid water. It's saturated and at 150 degrees Celsius. Now we have some heat coming in that causes it to expand isothermally until it is all saturated vapor. So stage 2, piston rises. And now we have water vapor. And this is still at 150 degrees Celsius. Then, in stage 3, we no longer have any heat coming into our system, but the water vapor will continue to do work and the piston will continue to rise. And in here we have water vapor, but now we also have water liquid. And this whole mixture has now cooled to 40 degrees Celsius. Now in step 4, now here we have some Q out, and the surroundings will now do work on the piston. Piston compresses the mixture inside, and here we still have a mix, so we have some water vapor and some water liquid, and this is at 40 degrees Celsius. And then the system continues to get compressed isentropically, and we return to state 1. So here are our 4 states. Now, here, so in usual problems with the Carnot cycle, we're dealing with an ideal gas. In our PV diagram, as you've seen many times, looks something like this. We're dealing with the saturated, in our problem, we have saturated water in our cylinder. So our PV diagram is going to actually look a little bit different. In our diagram, the process from 1 to 2, so here usually you will see a drop in pressure. The process from 1 to 2 happens isothermally and also at a constant pressure. When 2 to 3 there's no heat exchange, and this happens as usual isentropically. And again, sorry that's not really a straight line, but this process from 3 to 4 is also at a constant pressure. And then here we have our isentropic process from 4 to 1. And so this is what the PV diagram looks like for this problem. And that's one thing to note. And then our temperature entropy diagram will look really similar to diagrams you've seen in the past. So here we are at 150 degrees Celsius. And then 1, 2, 3, 4. This one is at 40 degrees Celsius. And from 2 to 3 and 4 to 1 are isentropic. So going back to the problem here is to find the temperature and pressure and volume at each state. So at state 1, 2, 3, and 4, I want you to find the temperature, pressure, and volume for each of these states. Then for each process from 1 to 2, 2 to 3, 3 to 4, and then from 4 to 1, I want you to find the heat coming into or out of the system, the work done by the fluid, and the change in the internal energy for each process. And remember your thermodynamic laws. Change in internal energy is equal to Qin minus work. And here we've defined work as positive when the system is doing work. System is doing work. And we define it as negative when work is being done on the system or when the environment is doing work on the system. So W as positive when the system is doing work. And so you'll be using this relationship and again the saturated tables for this part here. And then C is calculating the efficiency of the cycle using 1 minus Tc over Th. So this part is pretty straightforward as you've been given Tc and Th. Here, so in a past video, the definition of efficiency is the net work for the cycle over the Qin that was put into the system at state 1. And there's a whole derivation process from getting from this to this. So from your calculations from part 2, I want you to calculate efficiency using this formula too. And if you did your calculations right, this value should match up with this value. Okay, so why don't you give this problem a stab, and then in the next video you can see the solution in more detail, and we'll go through each of these sections. Should be, this would be. Okay, good luck.